set this up last week, and it did the thing where it goes, "Oh, did you set up a stream, buddy? Sorry about that."
Oh, yeah. I just started my stream.
Oh, okay. Sorry.
Oh, you're
I'll be
good.
right back then.
Anyone
Get right
tuning
into it.
in on Ether Cosmology, just bear with us for just a few moments, please, while Alan does a couple technical checks. I'm also adjusting my sound levels a little bit here still. But tonight, we will be doing reading and research. I will throw the standard disclaimer on the Thursday night reading that I tend to throw, is that this is not our goal here, is not primarily entertainment. We're not here to these are not polished presentations. Thursday night is about us doing live reading, live research, diving into papers, diving into topics, and it might not always be super entertaining. There might be spots where we're just highlighting documents or asking each other questions, but the idea is to give you all an opportunity to kind of look into how we do research and our approach to learning and our approach to diving into some of these topics. So yeah, thanks for being here. Please bear with us. And tonight we will be getting into the topic of optics. It does look like my streams are live, so that's good. We are live on Rumble, YouTube, Twitter, Kick, and Twitch.
Good.
For zero viewers
hello.
on Kick and Twitch, I'm sure.
All right, I'm back.
Excellent.
Right,
and are you live,
that.
sir?
Yes, sir. We are live. So we're going to get into it tonight. We're going to read a little bit about curved visual space and what that is. We've all been hearing a lot about it, and shortly hereafter, we're going to hear a lot more about it. So this paper will kind of get into a direct measurement of it. So we're going to look at that and the differences between the predictions of curved visual space and Euclidean geometry. And to give a quick preface on that, actually, now we'll get into it. We'll discuss the alley stuff later. Let's get into the reading. So this is going to go over an experiment of measuring curved visual space. So this is direct measurement of the curvature of visual space. That sounds very interesting. I wonder what that means. You guys see that okay?
Yeah.
Okay, cool. All right, so abstract. We consider the horizontal plane at eye height. That is, that all objects seen at the horizon, although this plane visually degenerates into the line of the visual field. The depth dimension, nevertheless, gives a two-dimensional structure. We address the problem of intrinsic curvature of this plane. The classical geometric method is based on Gauss's original definition. The angular excess in a triangle equals the integral curvature over the area of the triangle. Angles were directly measured by a novel method of exocentric pointing. Experiments were performed outside in natural environments under natural viewing conditions. The observers were instructed not to move from a set location and maintain eye height, but were otherwise free to perform eye and head movement and body movements. We measure the angular excess for the equilateral triangles for the sides of 2 to 20 meters, the vantage position at the barycenter. We found the angular excess in deficits of up to 30 degrees. From the data, we constructed the metric. The curvature changes from ecliptic in the near space to hyperbolic in the far space. At very large distances, the plane becomes parabolic. 1 second, let me read this message from JT. Can hear me on space audits, you can hear me on space audits, but not on. Can you guys hear me on Discord?
Yeah.
Can you guys hear me on the stream, live stream? 1 second. Oh, it's because I'm lagging on stream or whatever.
Terrific.
Yeah, it'll sort itself out. Yeah, as long as you guys can hear me, it's fine. It's because I'm lagging on stream or whatever. It'll be fine. Okay. Let's see. So what we're discussing here is we have, if you if you break our vision up into curved visual space, right? What it would look like. Let's see if I have the diagram prepared. Sure don't. Give me 1 second. Actually, we'll just talk about it later. But anyway, basically, you have a near field and a far field, right? And then even further than that far field, there's a different type of optical compression that you experience. So what they're describing here is the different levels of optical compression that you'll see um, in relation to physical objects in three-dimensional space. So let's say, an object of a certain height is a certain distance away from you. How you will scale that object to fit in your 180-degree field of view will be based on curved visual space, right? And as that object gets further away from you, the proportionality scaling will change to make it fit accordingly. And then especially when you add other objects, like in the background, for example. So if you take a building, right, in your near field, right, a building will appear taller than mountains in the background, right? But we know that the mountains are way taller than the building, but the optical compression rates due to things in the distance versus things in the near field is going to scale proportional so that it all fits, right? So this is this is a description of the mechanism for that, right? So if you break your vision into near field, far field, and then things that are just completely at the horizon, right? All right, introduction. People routinely commit appreciable and typically systematic errors when asked to estimate geometrical positions of their environment from a fixed vantage point. Barato and others, 1967, 1976, 78, and Wagner in 85. This is not surprising in view of the fact that these geometric properties are only implicitly specified by retinal images. Conventionally, one distinguishes between the visual field and the visual world. Prenny, it looks like a French lad there. Toby, you got that one? Your boy Prenny?
Pirin?
Prenay? Oh, okay.
Pirin?
Yeah.
Wow.
Prenay? It's Prenay, Toby. Okay. 1970s. So the geometry of the visual field is that of the simultaneous presence of the variously colored patches. The visual world involves an additional depth dimension. Depth properties are specified by binocular disparities in optical flow. And they are.
Did we say who this guy was first?
Who's that?
Did we say who this? Gauss, isn't this? Is that what we're reading?
The dude? No. We're reading a. What is this? 2000 a paper from 2000 by Jan Codenderker.
Oh.
Kind of whiffed on the last name there, but anyway.
Okay. All right.
But yeah, this is the people that brought up that go over the Gauss stuff, though.
Oh, right. It's about Gauss. My bad. I was
hold on. Yeah. This is because this is how they. Right. Like when you get into well, how did they come up with curved visual space and like what math to use? Well, shout out to the homie Gauss. So anyway, we'll get into that as we continue. But yeah, this is their experiment where they measured that curvature, right? How they substantiated swapping that spherical excess into curved visual space to derive these two field or compression rates for the fields. Anyway, the geometry of visual space is that of the geometry of the visual field is that of the simultaneous presence of the various colored patches. The visual world involves additional depth of dimension. The depth properties are specified by binocular disparities in optical flow and are varied by a bouquet of depth cues. The former involve problems of correspondence simultaneously between the retinal images in case of binocular disparities, successfully in the case of optic flow, and the various prior assumptions, and no interpretations of the retinal illuminance structures. The latter involves such interpretations. Our experiments were performed in a natural environment, open in a field. Oh yeah, okay. So what they're talking about here, they're referencing the previous experiments done for curved visual space, which are the alley experiments. Now the alley experiments are super significant, and we'll get into that here in a minute. Let me show you guys a diagram. So what they have here, imagine you got your boy, the observer here, and this is a dark room, and you have a row of lit candles or lit sources, right? Just some light sources right here, right? And then you have a guy. So the object here is to line these up, is to line up this second row based on this row just by eyeballing it, because the whole room's dark. You have no reference, just this light source and this light source, and you're just kind of cross-referencing it, moving along the y-axis, right? And then on the distance alley, instead of aligning them long ways, you're aligning them like up and down. So you got an XY axis here in the dark, how they're doing their alignments. And then when they plot that out, if the X and Y axis intersect, that means that we see in curved visual space in Euclidean, because the Euclidean prediction is that the lines would be outside of, let's see, if the geometry is ecliptic, then the parallel lines are outside of the distance. Oh, okay. If the geometry is Euclidean, then the parallel lines and the alley distance are identical. So what that means is they would never intersect. It wouldn't be possible, because you would never see it in that. It wouldn't be an option for you to even perceive it that way. So what they discovered, and they started doing this in like around 1856, they started doing like different variations of this. So they knew about this for a long time. They just didn't really tell people about it or incorporate it very well. But throughout the years, this quote unquote alley experiments have continued, and that's what they're referencing. They're talking about the history of that, and they're saying how their experiment is done in broad daylight. So this is the difference. So like similar kind of reference, but they're doing it in broad daylight to give the full context of that, of what they were just talking about here with the depth disparities and the luminous structures and all that. All right. So our experiments are performed in the natural environment in an open field under bright daylight conditions where everything is in plain sight. No doubt the observers use large parts of the visual field to estimate the depth of the objects that appear on the horizon. When we mention points or lines, these have to be understood as mere formal abstractions, not reality. Since these were primarily interested in the depth dimensions, we limit our investigation to the horizontal plane through the eye. This plane appears as the visual line in the visual field, the so-called horizon of the observer. Of course, we have in mind geometry here. In reality, the horizon need not be specified optically, nor do we confine our research to points. The azimuth is measured along the horizon, and the dimension as a dimension that is measured in the visual field. The depth is the quality of the points on the horizon. Right? So
Wow.
would it be fair to say that what they're doing is they're kind of constructing a conceptual azimuthal grid and then taking measurements inside of that to see where the divergence and convergence reaches its minimum and maximums to fit things in your field of view?
Yeah. Sounds about right.
All right. And let me see if I have a quick visual on that to kind of see. Oh, I do. Nice. The little lad. All right, 1 second.
Just to make sure I understand the alley experiments correctly, the idea there is that those the placement that people perceive that those should go, those lights, they basically overestimate how far inward they should be placed.
Yes.
Okay, that makes sense.
And then the intersection, right? Did we get there yet?
On the other plane.
Right. So, oh god, gotcha.
So yeah, here's a. Sorry, go ahead.
Alley experiment quotes. I think I have 3 or 4 of them from Gleam. Let me get them real quick so we can see where we started.
Oh, nice. Yeah. Hit us up. Oh yeah. Shout out to Gleam. Give the quick history real quick because I didn't know about this, and then I'll give a quick shout out to Skylar who presented this paper.
So like this whole concept of non-Euclidean visual space, as far as I can tell, started with this guy on the internet named Gleam, who's like a music producer and kind of a reggae, I think, a song artist who puts out awesome stuff. And he put these 10 quotes together from various accredited universities, all regarding Euclidean visual space in different ways. Some with an art museum, some with perspective, some with drawing, just all sorts of stuff that generated curiosity in people like Wissit and me who wanted to go look into it. And of course, Alan and everyone who started to think about the the differences between what we could perceive and how we could quantify it. And I think that he started us on the path that led us to right here. So, shout out to Gleam.
But isn't it also crazy, like, the fact that, like, it's super intuitive? Like, you literally can't get through a middle school art class without learning about train tracks converging, and that's, like, kind of the fundamental building block of all of it.
Yep.
Yep. So, yeah. And with that said, shout out to Gleam, and then shout out to Skylar, who, when we were all, hearing about this curved visual space situation, he found this paper, and I've read it, several times. And every time I read it, like, I learn something more from it. And it turns out that this paper is going to be super pivotal in future arguments moving forward, in relation to how they mapped the sky to the ground and then told everyone we live on a curve. So shout out to your boy Skylar, who hit us from the, still having a major impact.
The further ether, man. Yeah, hell yeah.
Yep. All right, cool. So let me see here. So we got so that's the visual. So this is what they're talking about conceptually here. The divergence and convergence that goes on in this visual field, and your ability to perceive the physical location of actual objects in this field of view, right? So, all right, we'll continue on. Then let me make sure. Is it back on the? Yes, it is. We're good. All right. All right, visually perceived, that is, depth, usually has been studied under tightly controlled conditions in the laboratory. Such conditions typically involve extreme stimulus reduction, say few luminous points in the dark, nothing else visible, intensities carefully balanced. So that's what we were just covering with the former alley experiments. Extreme response reduction, say a forced binary choice, the extreme reduction of viewing conditions, say fixed head, probably a bite board, at least a chin rest. So if you've ever been to the eye doctors or whatever, when you're doing the eye exam, a bite board would be that, I'm assuming, right? You just put your chin on it. So it's like basically keeping your head in a fixed position, and then monitoring how your eyes, move to adjust. Let's see. And probably fixated on instructions. Possible fixation on instructions. So yeah, that was actually something that was mentioned in a couple of these other papers, is that sometimes the what would you call them? The experimentees, the volunteers or whatever, they would get confused by the instructions, and there was like a whole thing with that. But yeah, when you find people that are able to follow through without hesitation and all that, it's anyway. So under natural conditions, most of these constraints are violated. Natural conditions are indeed the opposite of stimulus reduction, restricting viewing conditions, and also at odds with a natural setting. In our case, we constrained the location of eye height, but left the observers quite free to make head and eye movements and torso body movements. Even turning on the spot was allowed. We also designed a task that felt much more natural to the observers than a forced binary choice. From the applied perspective, so yeah, these guys really did their due diligence and like looked at the history of alley experiments and like the critiques of them, right? And then now they're applying a future, that knowledge in their experiment. So very cool. So from an applied perspective, such studies under natural conditions are obviously desirable. The scientific value, however, might be less obvious because such studies are less controlled or controllable than laboratory studies. The potential value of the studies in the depth perception in natural environments arises from the likelihood that the observers may change tactics when granted additional freedom and optical structure. Strictly controlled laboratory studies, however, cover only one part of the story. The larger part of the theory, yeah, my YouTube crashed. All right, yo, I'm gonna reset my internet real quick
Dang, okay.
because it just keeps doing it. I'll be right
That's
back.
a bummer.
Sorry.
Oh, you're good, man. No, you don't need to apologize.
I thought we were going to read. Actually, no, this is the one. When we backwards engineer spherical excess. It's going to be wonderful. It's like, hey, you know that thing that you think is on the ground? We can manufacture it based on optics. Okay. Yep.
Yeah.
You know that Samuel Robotham wrote like way back when that's exactly what they were doing. I just started reading that book, and he was like, these people essentially are spherical excess, and they look through these giant lenses with the curved bottom, and he's like, they're manufacturing curve out of the bottom of their lens. And I was like, that's not untrue, Samuel. They have a curvature button today, so it got much worse, unfortunately.
Yeah. Yeah, it's just I don't know. It was convenient for trying to make a case for the heliocentric model.
It's like it's its only use, isn't it? I find that suspicious, but whatever. Honestly, dude, reading these papers like a year ago was useless because nobody even understood the concept of changing Euclidean. They were just like, no, orthographic, this is it. No, what do you mean? No, there's no other option. You can't do that.
Well, I remember when I first started to really realize it was when I saw like MC Tunes, like I saw a lot of the Globers trying to use optics to make like assertions about like the flatness of the plane, and I knew intuitively just like, no, I've like done enough photography. I understand that like a photographer uses different lenses for a reason, and like it's just a matter of fact that you can't take in light infinitely in all directions, so you have to take into account your field of view from your single point in space. You are at a single point in a 3D world, so you are just inherently limited to take in light through that one single point, and that just necessarily creates a shape around you intuitively, like simply put, a sphere, but it's a little bit more complicated than that because of the convergence of your two lenses of eyes. But yeah, like I remember like that was one of the first things where I was like, something's not right here. These people are not the people making the argument for the curvature. Don't even seem to understand how optics work. Yeah, and then you get to this point where it's like, oh, not only do they not understand how optics work, but the actual science about it is for some reason absent from a lot of discussions specifically about flat Earth. Huh.
A lot of basis assumptions going on and collative things coming out. It's really weird. It's like proof of sphericity all of a sudden. Oh, you have a curvature projecting device? What? What the hell? What do you use that for? Geodesic surveying? What's that mean? Well, you survey up to 100 yards and then what? Or 100 miles with regular surveying, and then what? When are you surveying over 100 miles? You're not. You never get the hell out of here.
Yeah.
Bro,
All right, I'm back. Sorry about that.
Do it up.
All good, all good.
Riemannian or Mannian manifold.
What?
Just want to talk about it.
It means it's
in the
curved.
paper.
Oh, Riemannian. Yes. That is a wonderful shape.
Yeah. Basically a square over a fucking half a sphere. Essentially.
Ellen, it
Look
looks
at
like
it
you're
now.
trying to share, but it's not coming through.
Oh,
Yeah.
gotcha. Yep, I need to start a new one.
But look, this is
There we go.
this is
There
that
we go.
manifold
All
that
right,
we're about
cool.
to get into.
Let me pull up my YouTube chat real quick. Actually, don't need it. Okay, ready?
Ready.
All right. Sorry about that. And you guys can see it now?
Yep,
Yep.
all good.
Okay, so we were going over the history of, let's see, what was it, alley experiments, and how they were going to do a slightly different, or how they were, or how what they were doing was different in comparison. So the large part of the theory of depth perception is based upon the geometrical analysis of the bicentric perception of Helmholtz 1867 and Lundberg in 1947. This is only natural in view of the fact that binocular disparities is about the only cue left to the observer in the severely controlled conditions in the luminous points of the dark. There appears to be some consensus that the geometry of visual space, mainly that of the horizontal plane of the eye, is governed by Riemannian, or what is it, Riemannian?
I can't
Riemannian?
say it.
We all said it differently, so I think
No,
it's
you all said
I'm
it
gonna say
differently.
fuck it.
Well, I liked how Beastically said it. What did you say earlier?
Pick our favorites.
That's my
Riemannian.
No,
Romanian.
I don't.
Yeah,
That doesn't sound like Ryman. I think I'm
yeah.
gonna go with
So
Ryman.
so the
Like,
ramen noodle metric is the global field of the local metrics, i.e., the metric may change from the point to point, and certainly is not Euclidean. So dude, imagine how crazy that is, Toby. So like you were saying, hey, maybe only in the horizontal plane do those train tracks converge, home dog. What do you think would happen if you rotated them vertically though? You think they? Oh no, wait, they still. Oh shoot,
Shoot!
shoot!
Oh, doggone it!
Dang, nabbit. Okay. So anyway, so yeah, maybe it's just this horizontal plane that intersects the old ocular there. So this is by no means the only theory, but it is persuasive. But its persuasiveness suggests that it might be of some interest in attempt to assess the validity of such descriptions in a more natural condition. We do not assume that the space is of constant curvature, since there are various reasons for that, or for doubt, even under controlled conditions. Shane, what would you say about how would you describe the curvature, like mathematically? Would you say logarithmically,
wow, what would I say there? Could you say it one more time?
hyperbolically, linearly?
I would say parabolically. Yeah, I would say logarithmically. I would say inversely. We could do just regular hyper. We could do just about anything linearly. I mean, which way do you want it? I think we can do it any which way. Well,
So it's actually that's really interesting. So any which way you want to do it, and then think of if you impose bandwidth restrictions on parts of your field of view where where there's going to be linearity in the curvature, right?
so like if you were to apply like a logarithmic scale to something, and then in the bulk of it, like in the first like 82% or something, and it would be that corresponds to be like 20 to 25 degrees. Not below that, you wouldn't find linear, but after that, to about 40 or 50, you definitely find linear. Like say, if you were to use it between the tropics at any point, that's the perfect angle for linearity of the logarithmic scale. And then when you get to the point where it would just about start to curve, they stop letting you use it, and you go back to other tables. So I mean, it's almost like they knew exactly what that was and how to use it.
Huh. Well, we're going to learn about Gauss here too, and see how that's tailored into it. So yeah, to be clear, there, what they're talking about is the different types of curvature, or that's what we were just talking about. Anyway, then how you would express it mathematically, right? So under these assumptions, let's see, turn on the performance your hand. Okay, we do not assume that the space is of constant curvature, right? Since there are various reasons to doubt that, even under controlled conditions. So, like we were just saying, there's obviously different levels of it, right? So they're not saying that it's a constant curvature. We do not assume that the space is. We do assume that the space is Riemannian and that it is isotropic. The latter assumption is natural when the observer is allowed the freedom to turn on the feet and perform arbitrary head and body rotations about the vertical. Indeed, one might say that isotropy is then enforced by the freedom. No visual direction is singled out. Under controlled conditions, this is different. Clearly, the straight ahead direction is special. Is special then. Under the assumptions, we propose to determine the intrinsic curvature as a function of distance from the observer. Oh, dude, that's crazy.
Yeah.
Yep.
The intrinsic curvature as a function of distance from the observer.
Wow, no wonder.
That
Wait, hold
sounds
on.
so familiar. Holy shit.
Oh, man.
Yeah. All right. So, let's see. From the observer, the notion of intrinsic curvature was introduced by Carl Friedrich Gauss in a seminal paper, Gauss, 1980, dating back to 1837. Although the theory is arcane to psychophysicists, some of its consequences are relatively easy to grasp. Intrinsic curvature differs from extrinsic curvature. Example, a flat piece of paper remains intrinsically flat when you roll it into a cylinder or a cone, although its extrinsic curvature may change. The intrinsic curvature is evident for certain non-Euclidean properties of figures. One example treated by Gauss concerns the sum interior angles of triangles made up of geodesics, which are shortest arcs, or Euclidean straight lines. In the Euclidean plane, the sum is 180 degrees. Any deviation is called angular excess, which reveals the intrinsic curvature of the space. The excess is proportional to the area of the triangle. The excess per unit area, specific angular excess, is a measure of the intrinsic curvature. Notice that its physical dimension is 1 over length squared. Thus, the inverse of the square root, the absolute value, specific angular excess, has the dimension of length. So absolute value there, because keep in mind it can be, because it's Riemannian or whatever, I think it can be negative. So
Wow.
anyway,
So like
so they're
put
just
in, pulled out.
what's that? What's it?
Spherical excess pulled in, pulled out. Mathematically
Yeah.
pulled in, pulled out. Wow.
Yeah, essentially, right? So we'll see like the application of that after we kind of go over the rest of this example here. So Gauss showed that it simply equals the radius in the simple case of a spherical surface. So he's saying that if you apply this to the excess measured in a triangle, right, it will determine that that is the radius of the sphere that you measured, right, with your triangles due to the angular excess, right? So you can turn that directly. You can get a direct proportional relationship to spherical excess and in a radius. So keep in mind. So let's say hypothetically you had a specific radius in mind, and you were going to take measurements, and you needed a way to like get back to that radius, and then show everyone that, hey, these measurements I took are backwards compatible with this radius. That's crazy, right? Must be proof of the thing I'm asserting. So this would be like an application of how you could use that. So we'll continue on here with the example now. Here's a simple example. Consider a geographical triangle, Amsterdam, and then latitude, Boston, and Cape Town. This is a triangle of an area of 38,700,000 kilometers squared. From Boston to Amsterdam, it is 5,568 kilometers. And then Cape Town, 9,000 miles away, or 9,000 kilometers away, etc. The sum angle of the triangles is 234 degrees, 28 minutes, and 3 arc seconds. This differs appreciably from the 180 degrees. Thus, the Earth is significantly curved. The specific spherical excess is 0.00507 seconds of arc, kilometers squared. According to Gauss, this equals the curvature averaged over the triangle. 1 over the square root of the curvature equals 6,378 kilometers, which is the radius of the globe. So when you apply this angular excess, right? So if I pulled it up on what's it called? On Google Earth or whatever, mapped it out, you can see the big triangle they make, right? And they say that the angle difference of that gives a spherical excess of this, and then you apply your boy Gauss's curvature theorem there, and it gives you a length, and that length is the radius of the globe. Thus,
dude, no way.
yeah. Thus, we obtain the radius of Earth from the directions of the cities as seen from the other directions of the area of the triangle. Notice that the specific curvature is small. For instance, the excess of the equilateral triangle with sides of 1 kilometer is only 0.002 seconds of arc. Locally, the Earth is quite flat. So on your local scale, right, the Earth is imperceptibly flat. You could never quantifiably measure this on any scale or ever, right? You could only get it up over distances. And how are distances computed? Does anyone know?
Would it be on the ground? Not yet. That doesn't seem right. It's probably the sky.
Well, you would think it would be on the ground, but it turns out they do use the sky.
It's interesting. The curved sky. Okay, I'm with.
Yeah. Yeah. So, when Gauss was asked to perform geodesic measurements for his government, probably to increase the accuracy of military maps, probably that's one.
That's definitely it. Yeah.
That's one assertion that could be made, or one possibility, right? There's other possibilities as well. And he used this occasion to measure angular excess of large triangles between mountaintops. He found the values were not significantly different from zero and concluded that the space is flat with extents, with such extents.
Not significantly different from zero.
Dude called
Meaning
it
zero.
flat.
Dude,
Straight up. That's hilarious.
not significant. No, Toby, no. He called it not significantly different from zero.
It's a long way of saying zero. Though.
Huge distinction, dude. You got your zeros, and then you got your not so zeros.
Like,
very important distinction. Very important distinction.
The uni-field bipolar thing, or the uni-singular not bipolar field that they're running with. Like,
yeah.
Only these people come up with these ridiculously names that, like, I don't want to name the thing I'm working with because it might frighten me.
Yeah. So these non-zero distinctions here, or whatever, that may or may not be the same as zero. We decided to follow his lead and determine the angular excess of triangles of various sizes in visual space. For this measurement, it is simple to find the matter of intrinsic curvature of visual space.
Wow. I'm on board.
Sounds good. Let me sip some of this reading water real quick.
You can always popcorn if you want.
Oh, dude. Oh, I forgot about popcorning, dude. That's an option, huh? Let me let me tap out this. Let me get to page 4 and then we'll popcorn.
Okay, sounds good.
All right, hell yeah.
Do you give out Jolly Ranchers? My teacher gave out Jolly Ranchers.
No.
Oh, someone else knows about popcorn.
Dude,
I know.
I thought you made it up to confuse Shane and I.
Until right now, I was thinking that. All right.
Yeah, now we have independent verification. Yeah, if someone just popcorned in the chat too. It's definitely
All right.
Shout out to the popcorners out there.
All right. We implemented a simple, direct method to measure angles in visual space. To the best of our knowledge, this has not been attempted before. Closest is perhaps Ellis and others, 1991, although some investigators have used judgment of perpendicularity. I love that word.
It's a good one.
Nice. I get to use it back to back. Awesome. Perpendicularity is special, however, because it assumes an angular metric. For instance, perpendicularity is undefined in the projective or affine plane. We only require our observers to indicate the direction in visual space from one point to another, neither point coincident with the ego center. Pointing from an ego center is generally known as aiming, as pointing a rifle or a telescope, taking aim, or egocentric pointing. It is a task that can be fully performed in the visual field and involves no depth. Exocentric pointing involves aiming from a location distinct from that of the observer. A common case of judging exocentric pointing is in perceiving who looks at whom at a cocktail party. What?
So they're saying, like, because of the way curved visual space works, it's hard to tell, like, which way something is actually pointing, like which way someone's eyes are pointing, because of the way that your visual space is curved.
I see. Okay. We simply constructed a pointer that could be rotated by a radio link from the observer's position. The observer sees the target, and the pointer is instructed to rotate the pointer such that the position of the pointer, from the position of the pointer is aimed at the target. People find this a natural enough task to perform, By pointing from A to B, we essentially determine the visual direction AB as seen from C, where A, B, and C are all distinct. By this method, we determine angular excess of a triangle in visual space. All right, we're almost at 4 here. In this experiment, we propose to find the integral curvature, Gauss's curvature integral. It equals the spherical excess over the area of equilateral triangles with the observer situated at the barycenter. So literally an azimuthal grid. So taking your measurements and looking at them from a polar coordinate system.
It's almost like it's the most commonsensical thing to do ever.
By processing, dude, it's just yeah. Processing,
except for the dumb people today, it seems. For everyone else seems to have figured this out already.
And then made maps out of it. Processing of such pointing data should be trivial, since we merely need to follow Gauss's example. Shout out to Gauss, leading the way. The results do not imply a check on the Riemannian property of visual space. Any result is interpreted as the space variant intrinsic curvature. However, we directly address the problem of whether visual space granted as Riemannian character is a space of constant curvature. This is of some interest since it remains unresolved in the literature. Endow, 1991. The point is the conceptual interest because only spaces of constant curvature allow congruence, or the free movement of rigid bodies. This is indeed the heuristics behind Lumberg's hypothesis of constant curvature, 1947. All right, Toby, would you like to tag in, sir?
Nope, that's not how it works.
How do I do it? How do I gotta do it? Do I say popcorn?
You gotta pretend like you're trying to pick someone in the room. You go, popcorn, Toby.
Okay, that's so gay. I'm out.
All right. Popcorn, Toby.
Perfect. All right. We use a radiographically controlled pointer mounted on a tripod, see figure 1. The pointer was a white cube of 25 centimeters edge length, pierced with an arrow, shaft thickness of 1.5 centimeters, total length 125 centimeters. The arrow stuck out at 50 centimeters on both sides. The arrowhead was 6 centimeters long and 3 centimeters in diameter. The cube was painted white, the arrow bright orange. Okay, so there's the figure. Interesting. Okay.
Wait, a chick was doing all this?
Nah, can't be, dude. That's probably a witch.
Right.
So, figure 1, photograph of the equipment. Notice that this is a mock-up. In the actual experiment, distances were generally larger, a smaller sphere was used, the bottom halves of the tripods were lost in knee-high weeds, and the horizon was more distant. The photograph provides a good idea of the target, specific sphere at the right, the pointing device, the cube pierced with an arrow in the middle, and the task of the observer at the left. The observer held a transmitter and thus controlled the pointing device directly while looking back and forth between target and pointer. Notice the absence of any head constraining device, biteboard or headrest. The observer was even free to turn on the spot. Also notice that the equipment was not conducted in the dark and that the target and pointer were not isolated luminous points, but offered a number of monocular cues next to binocular disparity. In the Lundberg blank tradition, the paradigm is sufficiently reduced and controlled. However, it is perhaps somewhat closer to natural conditions. Can we scroll back up and look at that real quick again?
Mm-hmm.
Interesting. So I wonder what that remote is doing.
Which one?
In her hand.
The one. Oh, so it turns that arrow pointer to the
okay.
Yeah.
Interesting. Okay, cool. The transmitter was a standard Futuba F16 and yielded precise control over the orientation of the pointer. Targets were bright orange spheres mounted on thin steel rods, themselves mounted on tripods. Sphere size was different for the various distances. The spheres subtended 20 plus or minus 4 minutes of arc. Both pointer and targets were always at the eye height of the observer. Experiments were performed in an unkept meadow with weeds growing up to knee-high and even waist height. Thus, it was typically not possible to see the base of the tripods meet the ground plane. The meadow was an open area with some distant trees and buildings visible, but no obvious landmarks. During the experiments, we met with bright weather, mostly blue sky with less than 1/8 cloud cover. In the course of the experiments, the sun's direction changed appreciably. The observer was instructed to keep the feet on a small platform and to stand upright at all times. The observer was permitted eye movements, head rotations, and torsions at the waist, even changes in the placement of the feet, turning on the feet. The explicit instruction was to point the arrow to the target, i.e., to point it in such a way that someone at the pointer and using it as an aiming device would agree with the setting. Since the observers were not at the point, this is exocentric, pointing, not aiming, this was not easy. Though most observers found the task quite natural one, at no time were the observers informed of their settings. 3 observers participated in the experiment, the authors. All had normal acuity with binocular stereo vision. Layouts of positions was done with conventional geodesic aids, measuring tape and theodolite. Locations were accurate to 10 centimeters, pointer orientations to about 1 degree. This turned out to be sufficient given the repeatability of the observer's settings. The experiment. The experiment itself was straightforward. The observer was positioned at the barycenter of the equilateral triangles of various edge lengths. Okay. The pointer was placed upon one vertex, the targets on another vertex. We always averaged over settings in which the target and pointer were interchanged, thus assuming left-right symmetry. This technique obviates the need for an absolute calibration of pointer orientation, thus increasing accuracy. We also had the observer point at himself or herself. Point at himself or herself. This effectively calibrates the pointer orientation absolutely. Given this absolute calibration, we were in a position to check on left/right symmetry. We found no traces of left/right asymmetries throughout the experiments. We averaged over symmetrical cases in order to simplify later analysis. The data are then simply pointer orientation as a function of the size of the triangles. Since the target and pointer were at an angular distance of 120 degrees on the horizon, all observers found it necessary to make body and head turns in order to look back and forth between them. Okay. The essential pointing geometry is shown in Figure 2. Here, the observer at V points the pointer P, so the observer at V, the pointer P at the target T. The vertical pointing, that's a funny way to spell vertical. Does that mean the same thing as vertical?
Vertical. Yeah.
The vertical. Yeah.
Gotcha. The vertical pointing angle. Is that mu? What is that one? Or no, that's rho?
It looks very rowy to me, but I'm not sure, to be honest. And then what this bad boy is, I have no idea. So,
all right, so pointing curly P depends on the arc. Curly V between the pointer, or curly U, I'll say. So curly P depends on the arc curly U between the pointer and the target on the radio of their distances. RP divided by RT. So we have the tangent of the curly P equals the sine of the.
I wonder if it's a lowercase theta, because it's it's an angle. They always theta angle, so it's probably a lowercase theta.
Okay, so the tangent of theta equals the cosine of the curly U over RP divided by RT minus the cosine of the curly U.
This part's pretty good.
The pointer is illustrated in... Yeah, I'm curious how they ended up doing. I'm really curious, actually. The pointer is illustrated in 2 orientations in Figure 3. Notice that apart from binocular stereo, various monocular cues are available that might reveal the orientation of the pointer. For instance, the ratios of alpha divided by whatever that is, with a line over it, or lambda divided by L minus lambda could be used, etc. Estimates suggest...
One minus lambda.
What's that?
One.
Oh, what did I say? Oh, I said L. Lambda divided by 1 minus lambda could be used, etc. Estimates suggest that the monocular cues probably dominate at all distances, with the possible exception of the closest one.
So this is the first time they're trying to do depth visual
in this
space
experiment,
analysis and saying, hey, what we have isn't working.
Oh, gotcha. Okay. In this experiment, curly U equals 120 degrees, and RP divided by RT equals 1. Thus, the vertical pointing angle curly U is 30 degrees.
Theta. So this is, if I remember correctly, Eric said that when you have a line over it like that, that's like the average of it. So alpha over the average of all the alphas added up.
Gotcha.
I guess.
Okay.
All right. Okay, so then we have our pointer, object, observer, and then he's using radio transmitter to move this to point to that. All right. And then yeah, so so here's our theta is the angle between right here and the pointer to the target. And then the V is the opposite. All
cool.
Right.
Oh, so the pointing geometry, observer at V, pointer at P, and target at T are in horizontal plane at eye height. Thus, the arc curly U is a distance along the horizon. The vertical pointing angle, we decided that on being
Theta.
Theta. Thank you. Theta depends on the ratio of distances and this arc. The pointer as it appears schematically to the observer. Gotcha. All right, so results. The data are expressed in terms of the angle subtended by the visual direction to the pointer and the exocentric pointing direction. Notice that the vertical angle is 30 degrees. We found that the actual values differ significantly and systematically from this value. In Figure 4, we plot the actual values as a function of the size of the triangles. Notice that the results obtained for the three observers are quantitatively and qualitatively very similar. Though different in detail, straight correlation yields R-squared values of 0.98 for AD minus JK, 0.69. I'm assuming these are the people that did the experiment, right?
I would assume so.
Cool.
Like the what do you call them? Yeah.
Yeah, so it's showing the differences between it too. That makes sense. Cool. So linear regression reveals slopes significantly different from unity and offsets different from 0. Deviations for AD are 75% those of JK, with a 2.3 degree offset. Those of JL are 48% those of AD, with 13.8 degrees offset. Who won, though? Just kidding. An intuitively satisfactory way to... like, one of them was closest, right? There had to be a little bit of a competition going on. It looks like it was... who's on the middle bottom? Oh, they did bad on past 20 meters. So anyways, or it looks like JL was the man or the girl, whoever it was. JL did pretty good. In any case, I'll go back up. Can you go up a little bit? Sorry. I'll read.
Oh, yeah, sorry.
So an intuitively satisfactory way to represent the results is to use the fact that 2 points with directions attached to them define a unique circular arc. When we draw such arcs for the triangular configuration in Figure 6, we notice that triangles in the near... and so real quick, Figure 4 is systematic derivations of the pointings. Standard deviations are... Go ahead.
So, like, if this is them pointing and people can't really point well, what does it say for people lining up theodolites across fucking 100-mile and chasms and taking shots?
Yeah.
What do you guys think? What do you guys think that means?
Yep, and trying to
I don't know,
use
I
any
just-
sort
I
of
feel-
landmark or like it's just all of it is yeah.
Free ball and aligning to the stars in the middle of the woods. Okay, go ahead, guys. Fine.
Just free balling it.
Free
Free ball
ball.
surveying. I like it.
So, figure 4, systematic deviations of the pointings. Standard deviations are indicated by bars. The dotted line is the vertical pointing. Notice that all observers commit very significant pointing errors. No surprise there.
People can't tell depth or anything, it turns out. Look at that.
Oh, JK did do pretty good, though. Hats off to JK.
It's got them perfect
Probably in the
oculars.
finger, I was thinking. Yeah, it's probably the better finger.
Scatter plots of the average pointings of individual observers.
So this thing, what do you guys make of this thing right here? This triangle. This is like the results representation visualization. It's got like a little curve to the bottom, and the mountain is curved would represent the angular excess. It's a pretty good way to see how it warped the triangle.
Yeah. Yeah, it's interesting.
And now we're like, okay, if you're making triangles and
It's
measuring
JK
excess, but
only.
like,
Oh, so you're saying like the near field and far field, the different levels of optical compression, how it would affect it hyperbolically, and then so the divergence and convergence is represented through. Yes, they're measuring this with a curved lens.
dude. So again, I've called you to Samuel Robotham, and like the whatever 1800 was like, hey, essentially, I'm paraphrasing. These dudes here are looking through theodolites and measuring Earth curve, but it seems that they're pulling Earth curve from the bottom of their lenses. That's the only thing I read immediately, and I was like, "Oh, this dude figured out surveying, geodesic survey. That's the trick. You got it." And this is also the exact same thing, right? Manufacturing it. Oh my god!
Damn, hold on, I gotta fucking swoop this picture real quick.
You're gonna have to explain it to people that you're gonna use it on.
1 second. Optics. Just, let's throw it in here. No. 1 second.
I like that most of my notes on this stuff will be Alan's.
There we go. Fucking triangle. Direct measurement paper. All right.
I thought you said direct measurement ether. I was like, I don't know how you're gonna swing that one. But good luck.
I mean, put me in a corner, dog. I'll fucking do it.
Right? Take a swing.
All right, let's see here.
I mean, the light waves. The light waves are propagating to your eyes. There you go.
Yep.
So yeah, I guess popcorn. Shane, do you want to read?
I suppose I could. Make it a popcorn though.
If you don't,
Did I say
if you don't want to, you don't have to.
I think I have my own PDF though. Look at that.
Oh, check you out,
Oh wait, that's another one.
guys. We read PDFs for fun now. It's over.
Yes, it's a thing. It's a thing that happens. So, like, you're gonna have to either like. So, what's gonna happen after this? Just so you're clear, if they are watching, I did put it out on Twitter. You're gonna have to go find papers that support Euclidean geometric precision at this level to refute anything we say, or it's gonna be another sit down and shut up situation, right? So I don't know.
Dude, no one. I brought proof that we see in Euclidean.
Yeah, it doesn't exist. Again, another. Secret.
I see the
Not gonna
world
find
from.
any. Doesn't
I see
exist.
the world from an omnipotent, like I can see everything from all. I'm all knowing, all seeing. Oh man, that's insane.
And again,
Oh, dude.
this is for fun. So like, wait until it's work time. You know.
Dude, before we wrap up, we're definitely going to read some arguments put forward by Lundberg on the hilariousness of Euclidean geometry expressing visual space.
Excellent.
Excellent.
All right. So you said I'll popcorn us out of here. So where are we at?
The red part there.
Red part here.
No, the top of that whole thing. The field looked inflated. That's where we are.
Gotcha. Okay, so this is the representation of the different curvatures of the near field and far field, and how they will affect the triangle as it gets further away. Cool. So the field look inflated Thus, there will be angular excess, where those in the far field, that's exactly okay. Those are in the far field look deflated, and thus there will be an angular deficit.
Boom.
Without any more calculation, the raw data thus reveals the optical space is ecliptic, positively curved in the near zone, but hyperbolic, negatively curved in the far zone.
So I'm not necessarily going to conclude their geometric conclusions. I'm just going to say that they noticed there was a difference and a need for a split, because I think there's some other people with some different conclusions that come along the way after this.
Yeah. Okay. So let's see. Scatter in the setting of about 1.5 degrees, which appears to indicate remarkably accurate performance. 4.1 Determination of the intrinsic curvature. In order to determine the intrinsic curvature, we proceed by finding the integral curvatures of the triangle. 1 second. Excuse me, I had to burp. Gauss's curvature integra. The integral curvatures simply equal the angular excess. That is 6 times the actual pointing angles minus 180 degrees. When we consider two triangles of different sizes, then the integral curvature of the larger triangle is the sum of the integral curvature of the smaller triangle, in which is contained in it, and the integral curvature of that complement of the complement of the larger by the smaller triangle. Thus, we obtain the integral curvature of the a lot of integrals of concentric triangles folding in on themselves. Let's see. So thus we obtain the integral curvature of the triangle stripes in various sizes by progressive subtraction of the integral curvatures. Since these strips contain only a limited range of distance, we obtain a measure of the specific excess, that is the intrinsic curvature, as a function of distance by dividing the areas into a triangular strip.
So wait, there's a picture that we could show right at that point. I think that'll sell that really, really well, right? Hold on.
No, yeah, hit me up.
Yeah, like a really good representation of exactly that, I think.
Pausing for incoming picture, lads. Actually, I'm going to keep reading while you dig that up. Okay. Okay, cool.
Get back to the chat. Hey.
Oh,
Right?
your boy.
Yeah, man.
Your boy. Here we go. So you can guys see that?
So we're going to really wind it back and read that section again, and we'll just look at this. Yeah.
Okay, let's see. Where were we at here? So, determination of the intrinsic curvature. In order to determine the intrinsic curvature, we proceed by finding the integral curvatures for the triangles, Gauss's curvature integral. The integral curvatures simply equals the angular excess, that is, 6 times the actual pointing angles minus 180. When we consider the two triangles of different sizes, then the integral curvature of the larger triangle is the sum of the integral curvature of the smaller triangle, which is contained in it, and the integral curvature of the complement of the larger by the smaller triangle. Thus, we obtain the integral curvature of the triangle stripes of various sizes by progressive subtraction of the integral curvatures. Since these strips contain only a limited range of distances, we obtain a measurement of specific excess, that is, the extrinsic curvature as a function of distance by dividing the areas of the angular strips. All right, so let's look at the image again here, Shane. See what they're see what are they talking about there?
It seems like they're saying that there's an intrinsic curvature when they're taking an optic measurement of things in the sky, and that intrinsic curvature can be seen right there. If you look at how we represent the sky in the lower right there, and anything in the sky would then have that intrinsic curvature. So naturally, a celestial navigation triangle with a sight line or whatever, an elevation angle to a star, then any applied trigonometric function would have this inherent curvature in it, you would think.
You would think that.
And also just note that the Globers have to make up one visible horizon to play on the celestial horizon, but whatever with the grounding horizon, when they take their angle to the fake tangent horizon, always remember to keep directional down from the perpendicular relationship to gravity because they have to have the geoid. So they can do all that shit in the left-hand corner, and that's why that's funny, and we can translate on the right. So
and then assume some kind of omniscient, infinite Euclidean perception from a single point in infinite 3D space.
Forever. Yeah, exactly.
Yes. That's all you have to do, really. I mean, that's it. Just make some basic assumptions that contradict reality, and then you can be on the globe. All right. All right. We're almost done here, lads. Let's see here. All right. So that was awesome. Great relationship established there. The curvature of visual space, when you turn it into a distance, you can use it to make a map, but thus that map will have intrinsic curvature because everything measured of it is an arc to the radius of the sphere that you derived it from. Thus, there will be an angular excess relationship that will allow you to find the radius of that sphere that you're using for distances in the first place. Very cool.
Important to note that this all is true even if you live in your head a globe. So really, you should be perceiving like a
double globe.
A double globe, yeah. It should be insanely, like it should appear smaller than it is, actually.
You should see toilet paper Earth everywhere.
Yes.
So yeah.
Right.
But you don't. You see flat, in case you guys forgot. You need refraction to manufacture curve.
Oh, so real quick, what was... Yeah, never mind. Thus far, the data processing is fairly trivial. The results are collected in Table 1 and Figure 7. Clearly... One second. Let's see. Oh, I forgot I have a mute button for that. Sorry, I'll get better at that. Okay. Clearly, the intrinsic curvature changes systematically with distance from the observer. Oh, no way. Lundberg's hypothesis that the human optical space has to be one of the classical spaces of constant curvature is not born out of the present setting. So Lundberg, real quick, he was hypothesizing that there was a constant curvature based off of, what was that, some Russian guy that had some theory about it. So the out experiments that he was doing in the dark led him to believe that there was a constant curvature relationship. But when you allow people to have, the freedom of choice to make the decisions, there's like it's a different relationship. It's not constant, right? It varies. Okay, so the table of the Gaussian curvature meters squared, calculated from the angular excess determined by equilateral triangle experiment. The first column contains the estimated standard errors in the curvature. Right.
It's almost like looking for a golden goose and you're like, nah, and then it just falls in your house and you're like, oh, I guess I'll take that. Thank you.
Yep. All right, so we got the Gaussian curvature, distance over meters. Let's see, the intrinsic curvature for the number of distance ranges for the observers, JK. From the scatter in the data, we find that the curvatures are typically very significantly different from zero, except for a certain intermediate range that is somewhat differs for our three observers. The geodesic surface. We shall now perform one other step of our data processing that is of a more complicated nature. Given the intrinsic curvature as a function of distance, we proceed to construct a surface that can be depicted and has the same intrinsic curvature as the horizontal plane at eye height. In order to do this, we need to add a dimension to the horizontal plane at eye height. This dimension is a purely formal one. It should not be confused with a vertical dimension of physical space, for instance. Yeah, dude. Like I love the preface to it. Like, guys, what we're about to show you, don't use it against us.
Dude, it's funny because I literally put this tweet out to the globulist and I was like, guys, come see what we're going to use against you next week in case you want to. So we'll see. I don't know. We'll see if they did, dude.
Dude, I love the preemptive beg for guys. It like you know how many people are gonna like hear our argument and go, it says it should not be confused with the vertical dimensions of space, for instance, explanation point. Dude, oh man, I can't wait. I'm extra highlighting this or whatever. How do I make it super red?
You're ready for the references because they're gonna say that you're stupid and that you don't understand the reference that you're employing without understanding what it is, where it was, or who said it.
Oh, awesome, dude.
It'll be tough to combat someone like that. What do you guys think?
So they asked us to not use it against them. We respectfully decline. The only value for this formal embedding of the horizontal plane at eye height is in the three-dimensional space is that it allows the visualization of the curvature. Oh, so if you rotate those train tracks you were talking about earlier to the verti plane, you're saying that this representation is going to show that, but also don't think of it as train tracks rotated vertically.
Wow.
All right,
Don't do that.
Got it. We're all on the same page. Okay. Let's see. We assume the surface to be a surface of revolution, reflecting the isotropic nature of optical space for an observer free to turn about the vertical. This is an approximation since the observers did not exhaust all possibilities or all possible head positions in any given task. However, it is clearly reasonable at a reasonable first pass. Would you say Wotu?
We may piece the geodesic surface from all the other. Like literally, we're gonna construct a geoid. Here we go.
Oh, I didn't even catch that. What does it say? This approximation is since the
Next paragraph.
Oh,
Yeah, I go a little faster.
okay. Oh, dude, you're reading ahead and then getting excited.
Sorry, man.
Yep.
Bruh. All right, because our data range-wise constant. Data are range-wise constant. We may piece the geodesic surface together from annular pieces of a surface of revolution of constant curvature.
That's a citation. Oh shit!
Spivak 1977.
We might want to grab that one.
Look that shit up. Jesus, man.
Yep.
Another curvature guy. Oh, we gotta look that shit up.
Yeah, that one's gonna be fun.
Dude, this is what they don't do. You gotta look up shit that's against you. Like we're scared of that, right? I'm gonna go look it up.
A little too red.
Is that a curvature test with a paper? Give me. I gotta see it.
Give. Dude, following up on the references that they mention and stuff is like always leads to gravy, dog. 100% of the time.
Like if you're lost and you find one, and then they have 30 sources, you have 31 sources now. That's how that works. It's great.
Yep. You just need one, dog. Get you in the door. All right. So one example would be a sphere, clearly a surface of revolution of constant curvature. However, it is important to appreciate that arbitrary bendings leave the intrinsic curvature invariant. Thus, a cone has the same curvature as a plane, namely 0, because a cone is obtained by bending the plane. Likewise, if you slit open a sphere by a meridian, you can bend it into a spindle-shaped body, and you can cut off the two polar caps and then cut it by meridian, and then open the sphere to look like a car fender.
What?
Oh yeah.
Wait, hold on. What did he just? So let's go back. Let's go back to spindle-shaped body. What's going on? What does spindle-shaped body even say?
I'm not even sure what the fuck he's describing at this point, dude.
Okay.
What shape is that?
So if you take a glob sphere, right, and just make infinite, if you dice it up like infinitesimally, right? Like as small as you can. Eventually, you're gonna get parallel lines. So you're saying that if you cut off the caps of the where it converges, right, the hardest on the glob, and you just keep refining it, you'll get what would be car fenders, right?
Car fender.
I think what they're trying to describe is like the grill of a car, like the vertical lines in the grill of your car. 'Cause that's what it would be if you did that to a globe. So I can only imagine he's talking about like the grill of your car.
Like it's like literally like a half circle. Okay.
Yeah. So, see, if you cut off the two polar caps, then cut it by meridian, you can open up the sphere to look like a car fender. Or wait, well, hold on. What the hell's a car fender?
Well, that's what I just had to look up. So,
yeah, maybe that's not even a. Car fender.
It's like a half circle with a dome, kind of. I don't know if he's talking about like what year was this paper written. You'd have to look up car fenders from cars during that time period.
The thing about rims.
Basically,
Oh wait, no.
it's like that.
No,
Yeah, there you go.
I'm kidding. Yeah, okay. I was looking at rims and I was like, okay. So if you cut open
It's like
a
the
globe,
piece over the wheel, kind of.
oh, it makes like a half heart,
Yeah, kind of.
right?
Yeah.
Okay, gotcha. All right, now
Some of
we all
them
know
are
what a
just like
car
circle
fender
or
is.
half circles too, though.
Dude, how many cars do you guys think I've worked on?
Same.
Right. Similarly, a variety of surfaces of negative constant curvature can be obtained from a similar pseudosphere. Oh no way, a pseudosphere, Shane. Can you show us what a
Holy shit!
surfaces of
Really?
negative? Yeah, can
Holy
you show
fuck!
us?
All right, let's get this on. I'm ready. Hold on. I can run the paper on the side.
We're
All
tagging
right.
you in, bro.
Oh, shit.
All right, so this is awesome. So
Wow.
forget that car fender thing. Similarly, the various surfaces of negative constant curvature can be obtained from similarly the pseudosphere. So we're gonna show you what that looks like.
Yeah.
Like car fender, we have no idea. Pseudosphere, we got you, dude.
Right. That's hilarious.
Dude, like you're all right. This is crazy. Hold on. Let me get chat. Someone bring this up, and then just know that will be important later.
All right. Do you want to give some commentary on it or no?
I don't really. I mean, so it seems to have a shape with all sorts of curves. Like, say, if you had like, I could fit a parabola in there, parabolic. I could do the inverse. I can do squared. We can do fucking what the hell's it called? Logarithmic. I think. And I don't see linear, circular. Like any sort of path or shape could probably fit in that shape. Oh, and hyperbolic.
I'm sure
Wait,
you
that's
could
not-
fit linear in there.
Oh man, I don't see any straight lines in there. Unless you do like a tangent. I don't know, probably. There's two straight tangents through it now, but we put that there. So that's a
Anyway.
wonderful shape, yep.
Yeah. Cool. All right, so that's the old pseudosphere. We apply the constraints that the angular pieces should join together smoothly. Even then, some freedom of bending is left. This can be removed by applying. Nice. Got to the mute button in time, lads. By applying a further constraint. We apply the constraint that the surface should be as close to horizontal as the origin as possible. It turns out that we cannot satisfy the latter constraint completely. The best solution is to use a conical singularity at the origin. A piece of a geodesic surface for observer JK is shown in figures 8 and 9. The geodesic surface of the other observers are compared. Geodesics, or the shortest connections between the pair of joints can be realized by pulling a string taut between the 2 points constraining the string fully to the surface. The projection of such strings of the horizontal plane at eye height will be curved. The construction of the geodesic surface and the geodesic triangles of the surface will projection of the exact experimental results. Thus, the geometric surface is one particularly intuitive way to represent the data. So, if we recall to the pseudosphere representation here, right? All the angles derived to produce the angular excess that they measured within the sphere can be like this is it. And they're saying if you were to lay this down flat and have a string tied to it in the center, and you pulled the string up to raise it, you'd get your boy over here.
Oh.
And this would represent curved visual space, or their experimental results on a geodesic.
Very cool. Wow.
Yeah. So, oh, look, yeah. Shout out to your boy.
Wow. Yeah. So the geodesic server. Okay.
Yeah. Let's see. So the geodesic surface for the observer JK, although in this rendering in the true scale, all the numbers are meters, the vertical and horizontal axis are identically scaled. This is not the surface of space we move in. Oh, no way. The vertical dimensions is purely a formal one. The units shown are in meters. So Shane, they're saying that we don't see in this. Are you? What are your thoughts on that?
Well, no, I think what they're saying is that the first picture, the shorter one, is like I think they're saying that it's more like the second picture than the first picture.
See, the true geodesic this
Not a surface.
Oh, I see.
It's that one's purely formal, and the units are shown in meters. And then what does it say under the next figure?
The geodesic surface for the observer.
So yeah, that's what the vertical scale expanded.
Gotcha.
So they're extrapolating, I think, the horizontal, what they figured out from the horizontal vision, and extrapolating that out to the sky, to the full length of distance you could see upwards.
Like almost like an infinite cylinder that converges. I mean, actually, that's exactly what it is. The geodesic surface can be used to predict geodesics between any pair of points. Consequently, this representation of the data allows the prediction of any exotrinsic pointing experiment on the basis of our present data. The geodesic surfaces of the three observers are similar, although different in detail, and they are compared in Figure 10.
Is this paper called Flat Earth?
Flat
Earth, a paper?
It says direct measurement of flat Earth. With respect to curved visual space, I think was the actual title. Figure 10. The geodesic surfaces for the observers are compared. The graph sections of the surfaces by the vertical plane through the origin. The units are shown in meters. The geodesic surfaces are surfaces of revolution by construction. Discussion. We have introduced a novel method to probe human optical space, namely of the exocentric pointing. We have used this method to address Lundberg's hypothesis that human optical space should be constant, negative curvature. This hypothesis is clearly falsified by our data. The horizontal plane at eye height has an ecliptic curvature in the near zone and hyperbolic curvature in the far zone, and the neutral parabolic distance is about eye height, or is about in eye height. About in eye height. Okay. Existing data have predominantly been obtained under well-controlled conditions, typically with stimuli reduced to few luminous points in the dark. Under such controlled conditions, the only depth cue left is binocular disparity. In most of our case, a far richer bouquet of the depth cues was available to the observer. Moreover, our observers were free to make head movements, no bite board, torsion movements at the waist, and were even permitted to turn on the feet. The task was clearly different too. Nothing similar to exocentric pointing appears to have been used in the classical studies. There is thus little reason to expect any connection between these data. After Lundberg's work, many researchers attempted to determine the curvature of human optical space, blank in 1953, 1959, Endow and others 1962 again, and then in 1963. Shout out to the boys, dude. And then they tried one more time in 1991. Eventually, more consensus was formed by Endow in 1991 that the curvature might in fact not be constant, and our data agrees with this suggestion. However, as said above, our observers almost certainly use different cues to perform a different task in very different settings. As remarked in the introduction, our experiment is to check the validity of the hypothesis of human optical space. Human optical space is validate the validity of the hypothesis that human optical space is fixed of a Riemannian nature. On the face of this seems unlikely, though invariably assumes in the classical work, but we have no independent check. In order to investigate the issue, we should attempt verification of predictions from our data that go beyond our data. The geodesic surface allows us to predict the results arbitrary exocentric curvature, exocentric curvature. Nope, added a curvature there that's not there. Arbitrarily exocentric pointing task. One prediction that can be immediately derived is very surprising indeed. Owing to the fact that there is a conical singularity at the origin, we predict that the points are diametrically opposite to the observer. Can be joined by two distinct geodesics. Thus, we predict that the observer would need to choose between two equally visually correct exocentric pointing directions from a semitop angle of the conical singularity. We predict a difference of 5 to 10 degrees between such equally accepted pointings. Thus, such an effect is in the measurable range, although such a prediction appears prima facie rather unlikely. We have an actual indication that such an effect may in fact occur. We hope to report on this in subsequent communications. All right, so that was the direct measurement of curved visual space by the lads.
Yeah, they definitely continued and expounded upon that. And look at all the sources. So we should probably note that I haven't noted that I just said so.
Yeah, we definitely got to hit up these lads here.
Yep.
And then let's see.
You know why it's never going to lose? Because every time we read a paper, we acquire 4 more homework pieces. And then it's like they're never going to get out of the hole.
Oh,
It's
Indo
never
T
gonna-
1991. Go down to Indo T 1991. We want to grab that one, I think,
Yes.
because that was where the general consensus is coming from.
Yeah. Good call. Good call. All right, cool. So let's see if I have a couple. Okay, so here's kind of. Oh wait, I have the actual fucking. Oops, sorry. I have the actual thing here. All right, do you guys see this?
Boom.
Nice.
Now, what would you describe about that? How would you describe that thing?
So, this is the separation of the near field and the far field, and the circle compression here, right? You can look at that as optical compression rates relative to that field, right? So if you're looking at an object that's at this distance, it's going to be scaled proportional to this circle, right? And then on the outside here, same thing, right? So
Wow.
that's all it's going through. It's just
So
it's
would
showing
that
you
be like
different-
the most accurate way to perceive depth with a binocular visual space and 3D visual that you could think of? Because I couldn't think of a more accurate way to do it.
Yeah, it turns out if you take the spherical excess that they, say that they measured the curvature of the Earth with or whatever, that reduces back to the curvature of the Earth. If you apply that to optics, you get this.
Right. And it makes sense because you have nearsighted people, farsighted people. They have different glasses, prescriptions, strengths. Clearly, you treat far field different than near field. No denying it. Therefore, why are you applying the same uniform nonsense to your perspective and portraying that shit for hundreds of miles? That's retarded. It's retarded. Come on, we have to come to our senses, okay?
Yeah, well said, man. So yeah, let's just play this out. So this is known as the Vith-Mueller torus. So to put that video into perspective, if you take your left eye and your right eye and you intersect a sphere in between them, like vertically, and you rotate it 360 degrees, both of those spheres, you'll get this. You'll get the illusion of what you'll see, right, is like lines of latitude and longitude in your optics. So, and then you could break that down into your near field and far field, and then you could describe the two different types of optical compression between those two. So the ecliptical, parabolic, and what was the other one? There was another one.
I think.
Hyperbolic.
Hyperbolic for when you're when you're at the horizon. So
Yep.
keep in mind when you're at the horizon, a whole different level of is happening, right? So
Clearly.
that's why when you do celestial navigation, for example, right? Let's take you know what? See if I can hit up your boy Excalibur and do something here.
Nice, dude.
Shout out to the boys.
Is that why you didn't want to learn inkjet? You're like, I have Excalibur. This is stupid.
No. Okay. Let's see. Okay, so for what would you call it? So for celestial navigation, let's say you're right here. Oh, oops. Can I get a straight line? Make it any? Can I make it a color that anyone can see? There we go.
That's a gay color. I object to that.
Well, whatever. So this would be like your zenith, right? And then you're measuring out at the horizon, essentially, right? So it's not really to scale. God damn it. Put it back here. Kind of make it look better. So they limit you to the start, like that bandwidth of your field of view perception, right? They limit the degrees you can use to for celestial navigation to derive the references. So they have this specific set of how you're going to perceive the stars, and how they move in relation to your location on the Earth. Does that make sense? I can envision this better in my head, but does this make sense to anyone? Like if you were to look out at the horizon, like looking up vertically, this like at the sky, essentially, this is like you would be looking in this range to derive all your celestial navigation.
Yeah, and that explains the curvature that you would perceive.
Yep. And this is really a 2D slice of a 3D like torus, really, because you're seeing in like a 3D field. Obviously, you don't see your own eyes, but if you whip that around and pull it out a 2D slice, we've put that to this paper and drawn a diagram to show the depth of it. But it would be obviously a 3D all around you, right? But I think it's easy to see.
Yep. All right, cool. Yeah, I just wanted to show that there because that's super relevant for what's coming up on Tuesday and Wednesday.
Nice.
So I think if there's no questions or anything like that, I think we could wrap it up and then do promos for Tuesday and Wednesday.
Heck yeah. That was an awesome paper. Good choice, man.
Yeah, that was fun.
Yeah.
One of my favorites.
Thank you. Yeah, it's directly related to all relevant events, and then shout out to Skylar. He's the source of it. It came from him, and it's one of those papers that, like I said, I've come back to it multiple times, and then as I've learned new things, it's just like you're just like, oh no way, that relationship exists. Oh, that's how they do it. Oh, it's just So
yeah, dude. I mean, that's probably the most directly flat Earth paper I've ever read.
So also, there's this definite sign that now they knew about this sort of vision way before they told us about it, and knew while they were telling us other things, and knew while they didn't tell us before. Clearly, there's been some intent to not let this be mainstream. That's what I'm saying.
Yeah. So. Exactly, man. So Gauss, who we're gonna find out more in the next, in the upcoming presentations, has a huge role in this, and this is the guy who came up with that theorem that allowed them to produce a way for them to fix measurements to a specific spherical excess so that they could get back to reify the ground model that they're putting forward, right? That's derived.
It's a specific radius, yeah,
off of the sky. Yeah, it's like, so if there were going to if there was going to be a nefarious thing taking place, or even if it was just by happenstance, the way that all the math works out, it's like it just happens to be also equivalent to our optics directly proportional to our optics.
It's probably a coincidence, though. I bet
it could be either one, but
there's a lot of those. I think.
Well, to be a globularist, you have to be super into coincidences.
Super persistent, determined, tenacious.
But yeah, let's think we'll end on that. Oh yeah, so Tuesday and Wednesday there's going to be a back-to-back ether cosmology presentation. I'm going to be doing optics at 7, and then the following day Shane will be doing, what is it, like the lost history of the lost history of maps, and I don't know.
No, I'm not even going to do that.
We'll come up with something for it.
I think
it's related. Anyway.
Yeah, we'll do everything.
Anyway, we'll come up with something. But yeah, it's going to cover a broad spectrum of things, and it's all related to, optics directly. So
cool. Thanks, everyone.
All right. Peace.